Hi girls, today we're going to start with the Haykel. Let's start with objective 1. Apply the equation t equals to 2 pi square root of L over g to calculate the period of a simple pendulum for small angular oscillations. Now the period of a pendulum t is measured in seconds, and it is the time it takes the pendulum to make a complete cycle. So how much time it takes the pendulum to go from one point and return to the same point, passing through all points. This is called the period of a pendulum. To calculate the period of a pendulum, we must apply this equation. The period of a pendulum is equal to 2 pi times the square root of the length of the pendulum divided by the gravitational field. Now you can see from the equation that the period of a pendulum depends on two things. It depends on the length of the pendulum, and it depends on the gravitational field strength. So when the length of the pendulum increases, you can see that the relationship between it and the period of the pendulum is a direct relationship. Both of them are in the numerator. So if the length increases, the period increases as well. And it also depends on the gravitational field of the planet. You can see that the relationship between T and G is an inverse relationship. That means if the gravitational field increases, the period of the pendulum decreases. So it depends on the length of the pendulum. If the length increases, the period of the pendulum decreases. And it also depends on the gravitational field. If the gravitational field increases, the period, oh sorry, that's not correct. It depends on the length of the pendulum. When the length of the pendulum increases, the period increases as well. But and it also depends on the gravitational field. If the gravitational field increases, the period of the pendulum decreases. So for the length, it's a direct relationship. And for the gravitational field, this is an inverse relationship. Now let's solve some questions. Question 1, what is the period of, or question 5, what is the period of Earth, or sorry, what is the period of on Earth of a pendulum with a length of 1 meter? So what is the period he's asking for T? T is the unknown. On Earth, that means that G is 9.8. And the length of the pendulum given is 1 meters. So we'll write the equation T equals to 2 pi the square root of L over G, and then substitute using the calculator. So T equals to 2 pi the square root of L, which is 1 over G, which is 9.8. Using the calculator, so I'm going to multiply 2 pi multiplied by the square root of L, which is 1 over G, 9.8, equal, that's 2. So the period is equal to 2 seconds. For question 6, how long must the pendulum be? So he's asking for the length. How long will a pendulum be on the moon, where G is 1.6, so given G, and to have a period of 2 seconds, so given also is T. How long should a pendulum be to have a period of 2 seconds on the moon? Using the same equation, 2 pi the square root of L over G, the period given is 2 seconds, 2 pi to the constant multiplied by the square root of L. L is the unknown and G is 1.6. Using the calculator, 2.0 is equal to 2 pi times the square root of L, which is the unknown, divided by G, which is 1.6. And then you can press Shift, Calc, equal. So the length of the pendulum must be 0.16 meters to have a period of 2 seconds on the moon. Challenge: on a certain planet, the period of a 0.75 meter long pendulum is 1.86. So he gave me the length of the pendulum, and he also gave me the period of the pendulum. What is G for this planet? T equals to 2 pi the square root of L divided by G. T is given to be 1.8 seconds equals to 2 pi the square root of L. L is 0.75 and G is unknown. Using the calculator, you can do the same thing and solve for G. So 1.8 equals to 2 pi times the square root of 0.75 divided by G, the unknown, and then shift calc equal it to equal to 9.13 or 9.14. So the gravitational field on that planet is 9.14 newtons per kilogram. Now make sure that the units are always the length measured in meters and the gravitational field in Newton per kilogram, and the period must be in seconds for you to substitute in the equation. Question 8 says, explain why a pendulum is an example of a periodic motion. Well, a pendulum is considered to be an example of periodic motion because its motion repeats itself regularly. For a pendulum, it goes from one point back to the same point and repeats that motion over and over again. So it is considered to be as a periodic motion. For question 11 says, how must the length of a pendulum be changed to double its period? And how must the length be changed to half its period? So he wants me to double or half the period by changing the length of the pendulum. So these are two questions. The first question is, how must the length be changed so that the period doubles? So you must understand the relationship between the period and the length of the pendulum. Now the equation says the period is equal to 2 pi, which is a constant, multiplied by the square root of the length of the pendulum divided by the gravitational field. You can see that the relationship between T and the length is a direct relationship, and you can see that there's a square root on top of our length. So in order to solve any ratio question, you will place empty squares instead of the variables. So we have the time period. Now the 2 pi is a constant, it will not affect my ratio. And here we have the length is another variable divided by G, which is another variable. You can see that I'm changing the length and measuring the period, and hence G is kept constant. Because G is kept constant, I'm going to put 1 in the denominator. It does not change, only changing the period by changing the length. Now the first question, he says, how much would should the length of the pendulum be changed to double its period? So the period is doubled. I'm going to place 2 instead of T. Now, what should happen, or what should I change, or how should I change the length in order to double the period? So I'm going to search for the unknown x here, the factor that I must multiply the length by to double the period. So I'm going to place x in the unknown, which is how should the length of the pendulum be changed, or the factor that I must be multiplying the length of the pendulum by. So now using the calculator, I'm going to place 2 and then equal to the square root of the length of the pendulum, I want to find out what is the factor, so I'm going to place x. G was kept constant, so nothing happened to it. I'm going to pick 1. And then shift calc equal. You can see in order to double the period of a pendulum, I must multiply the length by 4. So to double the period, the new length must equal to 4 times the old length. I must quadruple my length in order to double the period. Now the next question, it says how must the length be changed to half the period? So using the same relationship, we're going to put empty squares instead of the variables. We have the period and we have the length in the numerator and the gravitational field in the denominator. Again, the gravitational field is kept constant. He says in order to half the period, what should I do with the length? So the equation is half equals to the square root of x, which is the factor of the length, divided by the gravitational field. Here the gravitational field was kept constant, so I place 1. Using the equation or your math skills, you're going to put 1 divided by 2 is equal to, equal to here. And then the square root of, I want to find out what is the factor of L that halves the period, divided by 1, and then shift calc equal. In order to half the period, I must multiply my length by 0.25, or in other words, I must divide my length by 1/4. So to half the period, the new length must be only 1/4, the 0.25 of the old length. In order to half the period, I must divide the length of the pendulum by 4. For example, if it was 16, now I need to reduce it by 16 over 4, like only 4. Alright.